Okay, great. Thanks. So you are able to see the slide, right?
Yes, sir.
Yes.
I can see your screen. I can see your screen.
All right. Can you see that CMI stochastic process, etc.?
Yes, sir.
Okay. And that is the only slide showing on the thing, right?
Yes, yes.
But I
CMI
am not
stochastic
able
process 1
to.
and then Markov chains written.
I am not able to. What is happening?
That is only page 1 of the slide.
Okay. So we will, in the first few lectures, we will review some probability. Something is not moving. Okay. So we will give a brief review of probability in the first few lectures. And the emphasis, since in this course, we will generally be dealing with discrete random variables. So the emphasis will be on discrete random variables, independent random variables. I had forgotten to write that there. And
Sir,
yeah.
so this meeting is being recorded, right?
Yeah.
You'll be posting on YouTube.
The Skype. I mean, not Skype. What is it? Last time also I did the same thing. I think it is
YouTube.
YouTube. Yeah. Sorry. I mean, my.
I have another class to attend to, so I might watch it later.
Okay, that's up to you. So.
Okay.
But only thing is now it has become more complicated to load it because earlier, that last 2 semesters, it was a course mainly for directed at one particular batch of students. So the bulk thing from the CMI email I could send. Now I have to send everything via Moodle, so which seems to be slightly more involved. Okay, so we'll try to manage. Yeah, so emphasis will be on discrete random variables, independent random variables, conditional probability, and conditional expectation. So these are the, especially conditional expectation, this you might see that many things when we briefly do some martingales later, discrete time martingales. So anyway, you will see as we proceed. And much of what I'm going to do today, you would be very familiar with, but still. So we begin with recalling what is the sample space. Just a second, why is it not coming? Okay, yeah. So here the capital omega, it is basically a non-empty set, and it is called the sample space. Yes, did anyone say something? This is regarded as the set of all possible events. That is all elementary events which either cannot be subdivided further or subdividing further will not serve our purpose. See, these kind of, these omega, etc. are chosen according to the context or the problem on hand. Okay. So, and the script A, which you see here, it is a collection of subsets of omega, and it satisfies certain properties. Again, you would have seen these things. The empty set and the whole space are in script A. So remember that any element of script A is a subset of capital omega. And if a set A is in script A, then its complement is also in script A. So it is sort of closed under complementation. And if, yes, you have a sequence of sets A1, A2, etc., which are all members of the script A, then their union is also a member of that. So that is
just one query, sir. So is the notes is available for after the class?
not just after the class, because I may wait for a particular this thing to get over so that I can supply it as one, one file. So sometimes it may be 2 lectures, sometimes it may be 3 lectures and so on. So if I'm going to supply all the notes then and there, then it becomes too complicated. The middle, see, I have made notes and divided into markup chains 1, markup chains 2, like that. And
Okay,
that
sir.
might require further splitting and so on. Or you will be loaded with something which will be covered only in the next class and so on. Okay. So let us
Okay,
see.
sir.
If I can supply the notes like that, I will not even bother to put it on YouTube. Okay.
Sir, I have a question regarding the last point.
Yeah.
So only countable unions are allowed? not
Yes,
arbitrary
yes,
unions?
yes. Only countable union. Countable union is allowed.
So arbitrary union of sets may not be in.
Yes, arbitrary union will not be there, generally.
Will not be there. Okay.
Yes.
And also the further clarification, this non-empty set which we call sample space big omega, is it a countable set or uncountable or anything?
It can be an uncountable set. For example, real line. It can be the real line.
Okay.
If you want to have further very basic things concerning many of these objects, you should attend a course on measure theoretic probability. Possibly at the end of that course, you may understand, or rather many of your questions, you will be able to see the answers. Okay. For time being, since that may not be possible, you can just take it that this kind of a thing, I could have just as well said that the script A is a bag of events. Okay. And the basic thing is, I will, and in the next slide or the slide after that, I will tell you the objective of this. But many of the subtle points and so on, you will be able to appreciate only after a 1 semester course of measure theoretic probability or measure theory at least. Okay.
So basically this big omega can either be countable or uncountable.
It can be finite also.
Yeah, it can be finite, but
Yeah,
it can also be countable.
It can also be infinite product space and things like that. Okay, so don't bother now. It can be quite complicated,
Okay.
depending on the context. Okay. So in this collection, this script A, for want of a terminology, it is called sigma algebra of subsets of omega. Don't bother about this term too much. It is all, these are all have origins in measure theory. It is just a bag of subsets of omega so that it serves our purpose. And any particular point in the original capital omega is called an elementary outcome, and any element of the script A is called an event. So these are again our convenient terminology. So as mentioned here, the script A generally is the collection of all events of interest for the purpose on hand. This for the purpose on hand, it is very, very important. Okay. So in other words, this script, this omega, capital omega and script A, these are in our, we have to decide what we should take. Or rather, if you are analyzing a problem, you need to sort of make a decision about these things. Okay. And usually the script A is a fairly rich collection of subsets of it. It is not generally very small, except in very elementary cases, perhaps.
That's so beautiful.
Okay. So this exercise will basically gives you one of the basic motivations for taking. Yeah. So if A and B happen to be events, then the complements as well as their union, their intersection and union of their complements and intersection of the complements, these are also members of script A. If A and B are in script A, all these guys again are in script A. And also, if you have a sequence of things in A and that countable union, this is of course follows from the definition of that sigma algebra, and this you can work it out. These are all basic theoretic equations you have to employ. So essentially, the idea of having this bag of events, the bag of events is such that all the unions, intersections, and countable union intersections are also in the bag. So for example, you know that event A or B occurs would mean we would be considering A union B. Events A and B happening simultaneously would mean A intersection B, etc. All those things again will be there in that bag. And for that, the reason is the probability P is generally taken as a function from that script A, which is a collection of subsets of that omega, into the unit interval, such that P of A is, you have to interpret it as probability of the event A. So that will be a number between 0 and 1 for every event. So all possible events are members of omega, capital omega. Therefore, P of this omega will be 1. Remember that omega is an element of script A. In other words, this makes sense because this capital omega is a member of script A. And similarly here, this empty set would mean something like an impossible event. So that probability should be 0. And the crucial assumption is this: if AN is a sequence of events such that these are mutually disjoint sets, that is, if I is not equal to J, AI intersection AJ is empty set. So A1 intersection A3 will be empty, A1 intersection A15 will be empty, like that. Then the probability of the union, that is at least one of them happening, is precisely the sum of the individual probabilities, which again you intuitively, it is familiar to you. Of course, all these things you would have come across in your first course on probability for math students, computer science students, TS students, and so on. Okay. So such a function is called a probability measure. And the triple is called the probability space. This again means that this is a kind of shorthand abbreviation. If you say that this is a probability space, then you know that all possible events are in omega, and this is a nice class of subsets of omega, and P is the probability, that is any member of script A, probability of A, that makes sense. And generally the probability space is chosen depending on the context, that is the problem under consideration. Okay, if you want to note it down, please do. Let's look at some elementary examples. Suppose capital omega consists of 4 points, which we shall denote by the way I write, you will be able to guess what this is about. HH, HT, TH, TT. So this sample space is a finite sample space. It has got 4 elementary outcomes. And script A is taken to be the collection of all subsets of omega. So that is, this is usually called the power set of omega. It's a collection of all subsets. And so that means this P, the probability we will have to say how it is for every member of A. So let us say we put the set consisting of just this point, HH. So let us say that is 4/9. The singleton consisting of only HT, as well as the singleton consisting of only TH, each of these have probability 2/9, and this one has this thing 1/9. So this defines how P is defined on this, the singleton set consisting of each of these things. And you know that any element of A will have to be disjoint union of these guys, these four guys. So P of A is given by this formula. Very simple. And all of you can easily see that this situation corresponds to 2 independent toss of a biased coin with probability of head equal to 2/3 in individual toss. This example is a very trivial exercise similar to this. What would be the probability space corresponding to 3 independent toss of a fair coin? Okay. So let us go to the next one. Example 3. All of you must be familiar with the standard deck of 52 cards, consists of 4 suits and so on. So let's say a standard deck of 52 cards is thoroughly shuffled, and let us say 5 cards are drawn at random. Cards are identical in size and shape. That's a crucial assumption. I mean, many of you will be knowing that some of these magical tricks involved. The deck is sort of rigged. All cards may not be of the same size, and so that it helps them doing magics. Anyway, some of you might even have seen such decks of cards. So, but this is a standard deck which consists of 52 cards, and each is distinct. And in this case, so since 5 cards are chosen at random, so from 52 you choose any 5. So there are 52 C5 possibilities. 52 choose 5 possibilities. So the sample space omega in such a case will have this 52 choose 5 elementary outcomes. This may be a fairly large number. This is a fairly large number. But however, still it is a finite set. And generally, when the case of finite sets, this script A sigma algebra is taken to be the power set. That is, excuse me, it is the collection of all subsets of that sample space omega. And this probability, of course, since all the cards are identical in shape and size, and we are drawing these things at random, one may assume that each elementary outcome may be considered to be equally probable. So since there are capital C number of elementary outcomes, each elementary outcome is likely to have probability 1/C. So for any subset of omega, P of A is 1 over C, or rather the number of elements in that A divided by the total number of all elements, that is capital C. I think you must have solved many problems in your earlier courses concerning this kind of a situation without perhaps bringing in all this paraphernalia about omega, AP, and so on. Okay, now let's go to next example. So in this case, the capital omega is taken to be x1, x2, xn, where each xi can be either h or t. So for example, x1 can be h, x2 can be t, h3 can be h again, and x15 may be t, and so on. So sort of this, what this means is that this capital omega is the collection of all n length sequences. So each of this kind of string, there are n members consisting of h and t. So you can easily check that this capital omega has 2 to the power n elements. So this sample space corresponds to the situation concerning when one tosses a coin n times. Each toss can result in h or head or tail. So all possible outcomes of that. If you are tossing the coin 15 times, this will have 2 to the power 15 elements, which is, it is a fairly large number, still finite. So since it is still finite, our this thing is that take this script here to be the power set. And suppose each elementary outcome, that is each singleton omega in this thing, has probability 1 over 2 to the power n. That is 1 divided by the total number of elements in that set. And immediately that suggests that for any subset of omega, P of A should be number of elements in A divided by 2 to the power n. You can easily check that this guy P is a probability measure. And as we all know that this is the kind of probability space when the problem on hand involves n independent tosses of a fair coin. If you want to jot it down, please do. So now let us sort of have a look at independent events. Again, something which you have seen in your earlier classes. So omega AP is a probability space. Two events A and B are said to be independent if probability of their intersection is the product of the probabilities. Something that you already know. Suppose you have now n events. So let us say A1, A2, AN, these are all events. So these AIs are said to be independent. If, see, for any, if you have any subcollection from this AIs, if you choose. So let us say that you don't choose all of them, but only K of them. K can be 1, 2, 3, etc. And choose that K, these things, let us say, according to this index, those things have I1, I2, Ik in increasing order, let us say, their index. Then probability of the intersection of these K guys, that is AI1 intersection AI2 intersection AIK, is product of the probabilities. That is P of AI1 multiplied with P of AI2 multiplied with P of AIK. I'm sure you would have seen this definition also in your earlier course.
So, sir, I have a question.
Yes.
So, if simply probability of A1 intersection A2 intersection A is given to be P of A1 times P of A2, P of
You will
A2,
soon see. You will soon see.
doesn't imply that the events
You
are
will soon
independent.
see. Please, can you just wait for some more time? Your question to be answered. Okay. All right. So let us look at some examples. Suppose capital omega is our good old friend. The first example we saw, that consisting of 4 elementary events. That is HH, H3, TH, TT. And let us say the script A is the power set of omega. And P is a number between 0 and 1. And let us denote by Q. Oh, I have put I here. It should be 1. Please make this correction. It is Q is 1 minus P. Yeah. So please kindly make this correction. I'm sorry. So this is our example 1 with P equal to, there we had taken a specific P, that was P equal to 2 by 3 or 1 by 3, something like that. This here it is a kind of arbitrary. So HH is given by P squared, that singleton HT and singleton TH, those sets, I mean, each of this is PQ, and TT is Q squared. And P of A is sum of P of omega, the singletons, as omega varies over script A. And as A, for any A in script A. Verify that this P is a probability measure, that it satisfies all those conditions we are given for a probability measure. These are all very simple exercises to sort of develop your these things, intuition. You can easily do that. Okay. So this space corresponds to the situation of 2 independent tosses of a biased coin with probability of head equal to P. Now let A1 be the event that the first toss results in head. And A2 is the event that the second toss results in head. So show that this A1 and A2 are independent events according to the definition given here. See, the point here is independent. When we say independent tosses, that is a kind of intuitive notion. We just want to convey to the other person how the coin is tossed. That is, the outcome of one does not influence the outcome of another, and things like that. And how to put that frame it mathematically means you will have to choose these probabilities accordingly. Okay, that is the idea. So show that you can easily show that this A1 and A2 are independent. So that sort of captures the intuitive notion of independent events. Again, a simple thing you would have seen in your earlier courses. So the next example, this is 6. So we go back to the situation of example 4. Example 4, it is this. So n independent tosses of a fair coin. So here omega is taken to be all these n-length sequences, and P of any singleton is defined by 1 over 2 power n. And therefore P of any A is the number of elements in A divided by 2 power n. So that is the situation. Okay. So let us denote by A sub I the event that the ith toss is ahead. For I equal to 1, I equal to 2, I equal to 2. Fix some I. And note that this event AI consists of all elementary outcomes where the ith toss is ahead, but all the other tosses are free. That is, it could be head or tail. There is no restriction. So it is easily, you can see that the number of elements in AI is 2 to the power n minus 1. The number of elements in A1 is 2 to the power n minus 1. The number of elements in A10 is 2 to the power n minus 1, and so on. Consequently, probability of AI by the recipe given in that example 4 is 1 by 2, half. Okay. So in a similar manner, for any finite number k less than n, and with I1 strictly less than I2, strictly less than Ik, all of them between 1 and n, their intersection, AI1 intersection AI2 intersection AIK, consists of all elementary outcomes with the tosses, only the tosses I1, I2, Ik resulting in head, while the remaining n minus k tosses may be head or tail. Okay. So probability of the intersection of these guys is precisely 2 to the power, the number of elements in this set is precisely 2 to the power n minus k. Consequently, probability of the intersection of all these things is 1 over 2 power k. So you can easily verify that these A1, A2, AN are independent as per the definition we had given. Okay. Now, we will make one comment, which I think I have made earlier. When we say that events A1, A2, AN are independent, what we have in mind is that if, let us say, A1, A2, A10 are independent. So if A3 and A5 happen to be heads, that doesn't affect how A7 and A9 should behave. So that is, occurrence or non-occurrence of any event among these has no bearing on the occurrence of any of the other events, or even a subclass of any of the other events. So we will illustrate this kind of point or this comment with two examples. Of course, these are all manufactured examples depending on the context or what you want to show. That is, in other words, this is going to be some kind of a counter example to say that here why independence cannot be defined by this kind of a thing holds only for if you say that k equal to n. That is not sufficient to guarantee independence. So take omega to be a 5-point set, 1, 2, 3, 4, 5. Let us say script A is the power set, consists of all subsets of omega. Suppose P is given by the singleton consisting of just 1 is 1 over 27, consisting of 2 is 8 over 27, and similarly for P3 as well as P4, 8 over 27. And this singleton P5 is 2 divided by 27. And any subset of omega, the probability is given by P of G equal to summation P omega, where omega varies over G. Okay. Note it down if you want. Now take A1 to be the set consisting of 1 and 2, B to be 1 and 3, and C to be 1 and 4. And you can easily check that P of A and P of B, P of C are all equal to 9 over 27, which is 1/3. P of A intersection B is 1 over 27. So P of this is 1 over 27. P of B intersection C is also 1 over 27. A intersection B intersection C is 1 over 27. So clearly, probability of A intersection B intersection C is the product of the probability of these three guys individually. So that holds. So that is that defining that equation for independence holds for k equal to 3, that is, and also equal to 1, n. K, in this case, 3 is n. There are 3 events we are taking. However, you can easily see that probability of A intersection B is not PA into PB. And similarly, this for the none of the other things, the equality holds. So A and B are not independent, B and C are not independent, A and C are not independent. It can also be checked if you want, A intersection B and C are not independent. So to bring out the meaning of independence, it is not enough just to stipulate that this holds. In other words, what that equation which we have denoted by club suit holds only for k equal to. So if you want, note down this thing, example, counterexample, very simple. And we will now go to the other extreme. Why not stipulate just this kind of thing holds only for any two guys from this. That is, it holds for k equal to 2, something like here. Pairwise independence. We will show that is also not good enough. So if you do it for any subset of that also, it's not good. Any particular subset also, it is not good enough. Or particular kind of subsets.
So basically, pairwise, mutually pairwise independence doesn't imply independence.
Doesn't imply, yes.
Doesn't imply independence.
Yeah, or even if you take 3 at a time or something, it will not, because then you can manufacture your own counterexamples. It may be more complicated, but it can be done. Yeah, I mean, such things.
So basically, it is necessary and sufficient to take all k from 1 to n, every value of k from 1 to n.
That is the definition. In this example, we show that to bring out the meaning of independence, not enough just to stipulate that this be pairwise independent. That is probability A in AI intersection AJ equal to probability of AI product probability of AJ for I not equal to J for all these things. So such a thing, if you say that, that is not enough. For that, the thing is, take omega to be a 4-point set, 1, 2, 3, 4, and A as usual is the power set. So each singleton has probability 1/4, and any subset G is summation probability omega as omega varies over G. So now suppose A capital, the event A is 1, 2, consisting of 1 and 2, B 1 and 3, and C 1 and 4. So you can easily show that probability of A intersection B is PA, PB. Similarly, P intersection B and C is PB, PC, and so on. However, if you take the intersection of all three, probability of A intersection B intersection C, that is precisely, this intersection is precisely A. So that is not equal to the product of PA, PB, PC. So the events ABC are pairwise independent, but the events ABC are not independent. Well, it's intuitively very obvious in this case. If you know that A intersection B has occurred, then it is automatic that C has also occurred. So A, B, C cannot be.
Shouldn't it be P of 1 instead of P of A?
Pardon?
Shouldn't it be P of 1 instead of P of A? However, P of A intersection B intersection C is equal to
P of 1? No, I don't understand what your question is. See, 1 happens to be in the intersection of all these things. The element 1 happens to be in the intersection of all these things. See, this kind of thing is a counterexample, right? That is, to disprove something, we are sort of manufacturing something. Okay.
Sir, I think he's talking about the third line. However, P of A intersection B intersection.
Yeah, that is. Oh, okay. So it should be, you are saying that it should be the singleton 1. Yeah, you are absolutely right. I'm very sorry. Yeah. So please, I mean, thanks for that pointing out this error. This, as our friend has pointed out just now, this should not be A. It should be 1, the singleton 1. Yeah. Thanks.
welcome, sir.
Okay, so yeah, I'm also happy that people are alert. I may be sleeping, that you should not afford. Okay, thanks. I think it's already 50 minutes almost since we started. So I think this, I would like to perhaps do it next. I thought I will also be able to do this. Success, we will recall certain things about what is generally called a particularly powerful model in probability and success failure experiment, Bernoulli trials. So maybe we'll take it up in the next class. I generally don't want to continue beyond about 40 minutes or so. If you are also writing down notes, taking down notes, it will be. Or if you want me to quickly run through, do you want it to be done? Yeah, maybe we'll do it so that next thing we can start something. So success failure experiment, again, you would have seen this model earlier. So P is a number strictly between 0 and 1. So n trials of an experiment where each trial has two possible outcomes. Let us say success or failure, maybe head, tail, and things like that. Or depending on the situation, you can declare what to be success and what a failure. And let's say probability of success in any trial is P, and probability of failure is 1 minus P. Yeah. So the appropriate sample space for this case is, it's a n length sequences, x1, x2, xn. And each xi is either an S or an F. So xi belongs to the 2-point set S, F. S denotes success, F denotes failure. Okay. So the number of elements in this sample space is 2 to the power n. So we shall denote by A sub I the event that the ith trial is a success. And Bi as the event that the ith trial is a failure. That's the complement of AI. So we have sort of said that these n trials are independent. So that is the basic thing about Bernoulli trials. The n trials are independent. What does it mean? So the crucial assumption in this model is C1, C2, Cn are independent events, where C1, for example, can be A1, C2 can be B2, C3 can be A3, like that. So each Ci is either an AI or Bi. So this is the assumption. Note that this assumption is basically an abbreviation for a collection of 2 to the power n assumptions. Like our saying A1, A2, An are independent, A1, A2, An minus 1, and Bn are independent. Let us say B1, A2, B3, etc., Bn are independent. Like that, if you go on, then B1, B2, Bn are independent. So this stands for really 2 to the power n assumptions. Of course, it's also clear that AI and Bi are complement of each other for any fixed I. So for any fixed I, AI and Bi are not independent. If you know that A1 has occurred, you know that B1 has not occurred. So this is just
what you just said. What you just said, can you repeat?
Sorry?
Can you repeat what you just said? Actually, I got disconnected.
What did I?
Regarding the
So he's
assumptions part.
asking,
The
Yeah.
above is a collection of 2 to the power n assumptions, that thing.
Yeah. So see, this is a kind of abbreviation for 2 to the power n assumptions.
Yeah, yeah.
Like A1, A2, AN are independent. A2, A2, B2, A3, B3. I mean, not A3, B3. A3, B3, you cannot. Like that. And finally, B1, B2, Bn are independent. For a fixed I, you know that let's say I equal to 1. A1 and B1 are not independent. So this sort of captures this collection of 2 power n assumptions, captures the intuitive notion of independent trials. Now let K be between 1 and n. You can easily see that probability of success in the first K trials and failure in the next n minus K. So that is A1, A2, AK, and then BK plus 1 intersection Bn. So that is the product of these probabilities because of our assumption. So that is P power K into 1 minus P to the power n minus K. And similarly, failure in the first n minus K trials and success in the next K trials is again easily seen to be this. So it is the same thing as this number, because there are exactly K successes and n minus K failures in each of these events. So now let x1, x2, xn be a particular sequence consisting of exactly K Ss and n minus K Fs. Then probability of that singleton set is P power K into 1 minus P to the power n minus K. Consequently, probability of exactly K successes in n independent trials is the probability is the same as probability of exactly K successes and n minus K failures in n independent trials. So there are n choose K ways in which you can choose such sequences, and each has its equal probability. So n choose K, P power K into 1 minus P to the power n minus K. This is your well-known binomial distribution. You would have seen in your earlier classes that independent Bernoulli trial, success failure experiment, etc. are tied to binomial distribution. Okay, I will overshot my time. I will sort of end this here. You want me to go to any slide for copying or anything like that? If not, I shall stop sharing. And okay, so today's things seem to have gone on reasonably smoothly. So I will end the session. Thanks a lot.
Thank you, sir.
Thank you, sir.
Thanks, sir.
Bye. See you.